conference. Our first speaker today is Vesselin Drensky from Sofia, and the title of his talk is From Commutative to Noncommutative Invariant Theory, Transfer of Results. So Vesselin, please start.
Okay, thank you very much for this one. I start with something which I think every know from the people in the audience know, but usually in classical invariant theory, one works with the complex numbers, but of course many of results hold for any field of characteristic 0. Also, the general linear group, it acts canonically on the vector space of dimension D, and then on the polynomial functions in a very special way. And of course, the algebra, the invariants of the group G, these are the fixed polynomials. But which are the main problems? This is, I think, clear for every one of you. To find classes of groups for which the algebra of invariant is finitely generated. Also to find explicit subgroups with the property that the algebra of invariant is not finitely generated. When the algebra is finitely generated, find the generators and the relations between them. Also, find conditions which guarantee that the algebra is isomorphic to a polynomial algebra. So it has a system of generators which are algebraically independent. Then, to calculate the Hilbert series of the algebra, to see where it is rational, etc. So this is, in other words, to say how many are the invariants of the algebra. Then, I'll state several theorems which are well known. The first is the classical theorem of Emmy-Noether, then Dierkheim-Satz, which says that for a finite group, the algebra of invariance is finitely generated. And also, the algebra has a system of generators bounded by the order of the group. Together with the Hilbert basis, thus, that every ideal of the polynomial algebra is finitely generated. Of course, you know that this is a non-constructive proof with a lot of discussions about this, that this is not mathematics, this is theology, etc. But nevertheless, this is something which is important. And as a corollary, if you have a finite group, then the algebra invariance is finitely presented. This means that finitely generated and with finite number of defining creations between the generators. Then the Hilbert series or the Poincare series of a graded vector space. This is a formal power series which counts the degrees of the homogeneous components. And of course, if you have an algebra of invariants, this is graded because every invariant is a sum of homogeneous invariants. So we can speak about the Hilbert series of the algebra of invariants. Here I should say the Hilbert-Serre theorem, which states that if you have a finitely generated graded commutative algebra, then the Hilbert series is a rational function of a very special form. Immediately you obtain that if you have a finite group, then the algebra of invariance has a rational Hilbert series. Of course, you can ask something more precise, and the Moulin formula, this gives also that if J is a finite group, then the Hilbert series is a sum of the inverse of some determinants. So I should state also the Chevalier-Shepard-Todd theorem that the algebra of invariance is a polynomial algebra if and only if the group is generated by pseudo-reflections or reflections. These are matrices which are with eigenvalue of multiplicity 1 less than the dimension, and only one multiplicity eigenvalue is the root of unity. And there are several equivalent conditions. For example, the group is a free-graded module over the algebra. So the polynomial algebra is a free-graded module over the algebra of the invariants with a finite basis. The group is a group of generated by reflections. The algebra of invariants is a polynomial algebra. There is also a stronger version when you have a reflection group, then the algebra of invariants is generated by homogeneous polynomials. The degrees, they are uniquely determined, and also we know the number of the reflections there. So this information can be useful when we study the invariance of some group generated by reflections. And of course, the next question is, which are the invariants of some concrete important groups? For the symmetric groups, everyone knows that the elementary symmetric functions, they generate the algebra of the invariants. But you have a more complicated question. You have several sets of variables, and you ask which are the invariants when the symmetric group acts on all these invariants. For example, if you see the original proof of Emmy Noether about her Endlichkeitssatz, you see that she uses this theorem. And the theorem of Schläfli, this is published in 1852, it states that if you have several numbers of variables, then the algebra of invariants of the symmetric functions is generated by the elementary symmetric functions and some polarizations. Polarization, for example, in the case of two variables, you have elementary symmetric functions, but you replace just part of the variables from the first and the other variables from the second part. So this can be used in the further considerations when we use two or three sets of variables when you act here. Of course, the diagonal group, it has a well-known algebra of invariants. If you change a little bit the coordinate system, you have that this is generated by two invariants, the product of the variables and the sum of the nth degrees of the variables. So this is was known already from the time of Riemann. And for our purposes, it's more convenient to assume that the general linear group acts not on the polynomial functions, not on them, but on the symmetric algebra. So you replace the general linear group with the opposite algebra, and then you get the same results, but the polynomials, they are not more functions, they are elements of the symmetric algebra. We need this when we study noncommutative invariant theory. So in noncommutative invariant theory, we should replace the polynomial algebra with something else. And the question is, which properties we can change? There are several branches of noncommutative invariant theory. One of them I am speaking about. This is, we have the following property. You have any commutative algebra, and you set the variables to the commutative algebra, and then extend this to a homomorphism. This means that the polynomial algebra is free in the class of all commutative algebras. So you have objects which are similar with this property. For example, the free associative algebra is such. This is the algebra of polynomials in non-commutative variables. The free Lie algebra, the free non-associative algebra. For the free associative algebra, there will be a talk in 2 hours by Sylvia Bumova about symmetric polynomials in free associative algebras, and you can see there which are some typical results. Our candidates here, there we replace the polynomial algebra with the factor algebra of the free associative algebra, modulo an idea which is invariant under all substitutions. So you take some elements of the free associative algebra and you replace the variables with these elements, and you get again something in the ideal I. So these ideals, they are called verbal ideals in the case of Lie algebras, or in the case of groups, or T ideals. Maybe you know that T comes from the famous paper by Specht about Gesetze in Ringen, where T is abbreviation for transformation. Of course, this is immediately related with the notion of variety of algebras. So, and these objects, they are relatively free objects in the variety of algebras defined by the polynomial identities of this ideal. There's some standard notation. I prefer to use German letters for the classes. And of course, in this case, if you study algebra of invariants, you have three parameters. One of them is the variety. And it turns out that many of the properties, they hold for classes of varieties, for many varieties, which satisfy a polynomial identity of special kind. The next thing, this is the group. Again, we have similar results for classes of groups, for example, for finite groups, for groups of reflections, for reductive groups, etc. The next thing, this is the rank, the number of the generators of the relatively free algebra. And of course, the interesting case is when you have more than one variable, otherwise you have the polynomial algebra in one variable. And again, usually if something happens for one number of generators, it holds for all number of generators. So the first question I want to discuss, this is an analog of the theorem of Noether, when we have a finite generation of the algebra of invariants. So the results are due to many people: Harchenko, Wolf, Ananin, Tonov from Bulgarian, me, Fisher and Susan Montgomery, Kemmer. Maybe I can add something more. So it's convenient to assume that the variety consists of unitary algebras. So yes, if the variety satisfies a non-matrix polynomial identity, so this is not the variety of all associative algebras, then there are many equivalence conditions, and if one of them holds for some number of generators, it holds for all number of generators. So the first thing is that the algebra is finitely generated for any finite group. And then we have that this holds only when we have one cyclic group generated by a matrix with two different or more different eigenvalues. Then the algebra is Wiki-Noetherian. Wiki-Noetherian means that assaining chain conditions for two-sided ideals. You have some more questions there. So since the presentation will be posted, you can see details there. For example, we have an identity of a very special form. For example, here we have the angular identity multiplied by the power of some element, another angular identity equals 0. Or you have something which starts with x1, x2, x1 in some power x3. And then, so you have x1 in the middle, x2, x3 in the end. And then you have things where you start either with x1 or you start with x3. Then one of these conditions is very easy. You take 2 by 2 matrix with eigenvalue 1 minus 1, and you check if the algebra of invariants is finitely generated, then this holds for all finite groups and for all size of the number of the generators. The next question, this is an analog of the theorem of Noether about the degree of the generators. Here we know that in the case of the polynomial algebra, the degree is bounded by the number of by the order of group. And here there is a theorem of Latyshev which states that if you have a finitely generated algebra which satisfies a non-matrix polynomial identity, then it satisfies a product of commutators. So the theorem of Matysh-Domokos-Me, this is that if the algebra satisfies the conditions for finite generation. Then the invariants in the relatively free algebra, they have a finite system of generators bounded explicitly given expression by the order of the group, the degree of the polynomial identity of a special kind, which we had above, and the class of nilpotency, this K here in the for the commutator ideal. And it's important to know that the Reynolds operator, which sends the polynomial algebra and also in the relatively free associative algebra to some elements with the property that the square of the Reynolds operators coincides with it, and also it acts identically on the invariant. So if you start with some element and you apply the Reynolds operator, you get an O invariant in this form. So this is funny that this operator appeared in the case of fluid mechanics, but now it's used more in our case than in mechanics, I think. So how to find the invariants when the algebraic invariant is finitely generated? There is some obvious algorithm. We apply the Reynolds operator for all monomials of degree which is bounded by the degree which we had with Matesh Domokos in our theorem. We applied the Reynolds operator and we consider the vector space. So there is an algorithm step by step which allows to find a minimal system of generators. And of course, if we know the Hilbert series and the algebra of the invariants, then as in the case of commutative algebras, the algorithm may be faster. So there is also an analog of the Moulin formula. The Hilbert series of the relatively free algebra, this is multigraded. So you have a Hilbert series which counts the number of each variable. And there is a theorem by Formanek. You take the eigenvalues of the matrices which participate in the group, and you take some sum where you replace the variables with eigenvalues times t, and you get the Hilbert series. By the way, it's easy exercise to see that if you start with the polynomial algebra, you get the Moulin formula. If you take the free associative algebra, this is also called there. In the Moulin formula, you replace the determinant by traces. And also, you all know that in the 80s, Kemmer developed structure theory of T ideals and used it to solve, for example, the Specht problem. But one consequence attained by Belov, or Kanev Belov, and then precise by Alan Berry, that if the variety satisfies a non-trivial identity, then the Hilbert series, the multigraded Hilbert series, is a rational function. So immediately from here, and the theorem of Formanek which we had before, says that this theorem here, that if you have a variety which satisfies a non-trivial identity, then the Hilbert series of the algebraic variants is a rational function for any finite group G. So the theorem of Chevalier-Chappell-Tott also holds in some special kind. This is a theorem of Matesh Domokos many years ago, that the algebra of the invariants is isomorphic to itself, to the relatively free algebra, if and only if the finite group is a group of reflections and the variety satisfies a triple commutator. This means that this is a subvariety of the variety generated by the Grassmann or exterior algebra. And of course, here you have an easy algorithm to find the generators. You take the generators of the polynomial algebra of invariants and you write them as element in the relatively free algebra. Simply you apply the Reynolds operator, there to see how these elements are there. Of course, if you have a concrete group, you can try to find some properties in the polynomial algebra which can be transferred in this case if we know that the relatively free algebra in some sense is close to the polynomial algebra. So which are close to the polynomial algebra. For example, if you consider the variety of the Grassmann algebra, which is defined by a commutator of length 3, the commutator ideal has a very nice basis. It starts with some monomial, then you have a product of commutators, and the variables in the commutators they increase strictly. So you also have additionally that if you take the product of some number of commutators modulo number of more commutators, this is a free module of the polynomial algebra. So how to find the invariants in this case for a finite group G? You have a finite set. You find a set of generators of the invariants in some module. The commutator ideal in degree k module, the commutator ideal in degree k plus 1, and you find a set of generators as a module of the polynomial of the invariants of the polynomial algebra. Then you leave these elements to the commutator ideal. You apply again the Reynolds operator. You remove the elements which are extra, and you obtain a minimal system of generators. So you can realize this very easily using a computer program, for example. And of course, here is the first step of the algorithm, to find a set of the generators of the invariants of the commutator ideal. Here you can do the following. The group acts on the vector space with basis the homogeneous elements of degree 2k, which are product of commutators. And you consider the polynomial algebra in two sets of variables. The usual variables x1 to xd, and this product of commutators. You assume that they are commutative. So you find a homogeneous system of generators. Then you take the generators which are linear in the variables, which correspond to product of commutators, and you find a set of generators there as a module of the algebra of invariants. So all these things, they can be solved explicitly and algorithmically easily. So in this direction, there is a paper, for example, by Erdogan and Van Dijk, which describes the symmetric polynomials of degree 2 and 3. Of course, if you start with any number of generators, you can find similar results for the symmetric polynomials. In the case of two variables, you can find the diagonal invariants, so you can do all these things relatively easily. And the next thing, this is the Mittobelian variety of polynomial of associative algebras. This is a product of two commutators as a defining relation. And this variety is generated by the algebra of 2 by 2 upper triangular generic matrices. So, and sorry, this is generated by the algebra of 2 by 2 upper triangular matrices. And the commutator ideal, it has a very nice basis. You have a monomial, and they have long commutators where the variables, they're ordered. The first is bigger than the second, and then they increase non-strictly. And of course, this is a left module, which is free of the polynomial algebra, because you can multiply by variables from the left. And if you take the adjoint action, this is also a right module, which is not free when you have more than two variables. And this algebra, it has a realization, the relatively free algebra of this variety, which is that this is generated by generic upper triangular matrices, but also it can be embedded in some algebra, which is something similar to the big and red product for Lie algebras of Schmelkin, And there is also some results on Jacques Lewin for matrix representations for associative algebra. These results, they are somewhere from the 60s and 70s in the previous century. So, from a algorithmic point of view, what is interesting here, you take the polynomial algebra, which acts from both sides on some free module generated by some variable z, and the multiplication in this algebra, this is, you multiply the polynomials in commuting variables in a normal way, and when you apply from the left and from right, you simply multiply by the polynomials. Here I have a misprint. X prime y should be x y d prime. In the second one, line from below. And the condition is that if you have these elements generated by z, the square is 0. So this algebra, this is a Mitabelian algebra, but which is more important, that it contains as a subalgebra the relatively free algebra of the Mitabelian variety, so the Mitabelian free associative algebra. And it's easy to see which are the elements in the commutator ideal of the relatively free algebra. They are images. They are simply of this form that if you multiply the j coordinate by the difference of the corresponding y's, you get 0. So this allows to find the algebra of the invariants for any finite group. You start again with the polynomial invariants and the invariants in 3 sets of variables. And then you find these generators which are linear in the set Z. And they form a generating set of the elements in the commutator ideal as a bimodule of the polynomial algebra of invariants. So then you lift these elements and you have to see which of them are in the commutator ideal, because you have something more. But nevertheless, you can solve this problem algorithmically quite easy. So in this direction, very recently we have a paper with Bianco Stadinov. This was posted in arXiv maybe a week ago, that if you take the generators x plus y and I and x minus yi, then the algebra of invariants of the diagonal group is generated by the elements which are non-zero modulo of the commutator ideal. You see, you have uv plus vu because you're in non-commutative case, and you have some other elements which are also at bounded degree. By the way, the Mitabelian variety, this is in the list of varieties for which the algebra invariant is finitely generated for any finite group. So if you want to have non-associative relatively free algebras, you have two obvious candidates which are close to commutative in some sense. One of them is the Mitabelian variety of Lie algebras. This is defined by a commutator of two commutators is 0, or in other words, this is solvable of class 2. By the way, in the old literature, Mitabelian means nilpotent of class 2. So, for example, in group theory, but now the more common expression is the Mitabelian means solvable of class 2. The next thing, this is the variety of bicommutative algebras, which is defined by a polynomial identities. This is non-associative, but if you have the product of two elements multiplied from the right by a third one, you can change the places of the second third one, and something similar from the left side. So what is the advantage of this? For the free Mitabelian Lie algebra, the commutator ideal, this is a module of the polynomial algebra with the adjoint action. But so you can make similar considerations as in the associative case, but you have a big advantage that you have only a module and not a bimodule. For example, with Van Dyck, Yogeshwu, we have found the invariant, the symmetric polynomials in the 3-meter billion Lie algebra. In the same paper by Boyan Kostadinov, which was published recently, posted recently, we have the invariance of the diagonal group. And for the free bicommutative algebra, what is the advantage? So this algebra, it has the property that its square is an associative algebra and commutative algebra. And the square is isomorphic as an abstract algebra to the product of two augmentation ideals of polynomial algebra. So you have two sets of variables. You have the polynomial algebras in one set without constant terms. You have the polynomials in the other set without constant terms, and you take the product of such things. So this means that if you study the invariance of the free bicommutative algebras, this is enough to see which are the invariants of the polynomial algebra in two sets of variables, or to transfer this immediately to the case of the free bicommutative algebra. So, of course, the very classical invariant theory, this is the invariant theory of the classical groups, the general linear group, the special linear group, orthogonal, special orthogonal, sporadic group, sorry, not sporadic, but symplectic group. And again, if you have some results there, you can try to obtain some results for relatively free algebras. Yesterday, there was a talk by Ivica Hristova, where she discussed some computational problems of this views and some other problems, so I don't want to enter details in this direction. I want to state only one example. You have a paper with Matej Domokos that if you have a variety of associative algebras, then the algebra of invariance is finitely generated for any reductive group if and only if the group satisfies the angular identity, or this is equivalent with the product of with the usual nilpotent condition. Of course, there are also some other things when you can speak about how many are the invariants, how to calculate the Hilbert series, especially for classical groups. But this is something which I think is better not to discuss now. Okay, thank you very much.
Thank you very much.
Okay, thank you.
Are there any questions? So I suggest just go ahead with your questions, because I may not see your hands raised.
Okay, so can I just ask, this is Jonathan Elmer, by the way, if you can't see me. Is there a like a canonical textbook for non-commutative invariant theory? Because I've never seen one.
Once again, please.
Is there a canonical? Sorry, is there a canonical textbook for non-commutative invariant theory?
You see, many years ago there was a survey article by Formanek, and also I had a survey article. It was published about 35 or more years ago. And since this is some journal, in some proceedings of conference, which is not available online, recently I posted it in archive. This is called Commutative and Non-Commutative Invariant Theory, or something like this. You can see
Okay.
So the paper was published in 1980s, 19 something, but it's posted in archive very recently. Also, with Formanik, we have a book about PI algebras. I also have another book which was published about 2000, which is called Free Algebras and PI Algebras. Also, there are some moments on invariant theory, in non-commutative invariant theory, but otherwise I don't know some paper, some books on this topic.
Yeah,
Of course,
thank you.
Okay.
Yeah, it seems to me like it's about time somebody wrote one.
Okay. By the way, one of my friends saw this abstract, this survey article from 30 years old, and told me, "Okay, recently I have 5 or 6 papers in the topic, and you have not included anything in your survey article." So I explained that survey article was written before.
Maybe I ask
Yeah,
one
sure.
thing. That, you mentioned this theorem with many, at least 10 characterizations of the varieties where all finite groups have finitely generated algebras of invariants, and you showed this simple criterion that a 2-element group has finitely generated algebra of invariants. So this looks simple, but is it really easy to verify in a concrete case that its algebra of invariants is finitely generated or not?
Okay, I don't know. In the cases where I have tried, this is easy. But in a general case, I don't know. But you see, in the case of 2 variables, you have a simple identity which you can check. If this is holds there, then this is okay. If it doesn't hold, then
So it seems that there are no more questions. So thank you, Vesselin, again.
Okay, thank you very much.
And I think we have 5 minutes to continue.
Okay.